Welcome friends to the Formula Engineering classroom. And in the last lecture we discussed about some types of different types of fluid flow. In this lecture we will understand the concept of linear translation, deformation, rotation and shear deformation of fluid during the flow. This topic is very much important to understand how the fluid particles are translating, dimensionally deforming or rotating and shearly deforming and all these things. And this topic is also important from the concept point of view, and through this one we can visualize how the flow is happening. So let's start. So in this concept, in all these topics, we first will try to understand what is the linear translation of fluid. So I'm saying first we are trying to understand the linear translation of fluid. Okay, so let's suppose we are saying this is our x and y axis, and we are considering a fluid element. Okay, we are considering a fluid element here. This is the center, let's suppose O here, and in this case we are saying the dimensions are dx and dy. Obviously I am considering a two-dimensional element here. Okay, now so I'm marking the faces here. This is A, B, C and D. So this is our fluid element, and we are simply talking about the linear translation. The term linear translation means the fluid element is simply moving from one point to another point or from one place to another place, and the dimensions remain same. Means in this case there is no deformation, no rotation, nothing. It's simply translating from one point to another point. So when will it will happen? So we are saying u is the velocity in x direction, and v is the velocity in y direction. I suggest you that make a notes of this topic, because mostly books are not clarifying all these things. So it's better to make a notes of this topic. So we are defining u is the velocity in x direction and v is the velocity in y direction. And I'm saying u and v both are not varying with with x axis and y axis. Means u is constant, okay, and this is not varying with the x and y, and v is also constant. Let's suppose this is c1, let's suppose this is c2. So u is not varying with x and y, and v is also not varying with x and y. So if we are saying u is the our velocity in x direction, so on the face AB we can say that this is our u. Okay, on the face AB, this we are defining this our velocity u here, and it is same throughout this face because it is not varying with y direction. And obviously as u is not varying with x direction, on the face CD the magnitude of this velocity will also remain same. So we can say that it will look like this one. It is looking like this one. Okay, so this value and this value both are u. Means u is not the function of x, also u is not the function of y here. Similarly, v is the velocity in y direction. So on the face AD I'm saying this is our velocity v here. So obviously v is same throughout the face AD because v is not the function of x. This is our v. Obviously v is not the function of y, so on the face BC it will also remain same. This will look like this one. Okay, this is our velocity v here. So you can see here u is not varying with x and y, and v is also not varying with x and y. So obviously in this case within some time interval, we are saying time interval dt. So in this time interval, this fluid element is going to shift from this point to some another point, and no dimension is going to be deformed because the velocity is same. In the y direction the velocity is v, that is not varying over here, and u is the velocity. In x direction this is not varying here. So this element is going to translate from this point to some another point, and we can say that it will look like this one. Let this is our element right now here after the time interval dt. This is our element new position. Okay, so we are saying this is o dash, this is a dash, this is b dash, this is c dash, this is d dash. So this is the new position. So you can assume this is moving along this streamline, and this is the position in the time interval dt. So now we want to check how much linear translation will occur in x direction in the time interval dt. So we want to check this distance, that is from the point o to o dash. We want to check this value. What is the linear translation in x direction? So we are saying the velocity in the action x is u and the time is dt. So this displacement will be simply velocity multiplied by time, that is u dt. So the linear translation in the x direction is equals to u dt, velocity into time. Similarly, we want to check what is the translation in the y direction. So this is our o here, this is our o dash here. So this value, so the velocity in the y direction is v and time interval is dt. So this is the linear translation in the y direction, and this is the linear translation in x direction. Okay, I think point is clear. Now the second part is linearly or linear deformation. Means now we want to calculate the deformation or linear deformation, or you can say that dimensional deformation of this fluid element during the flow, and we are saying this is linear deformation. Linear deformation means there is no change in shape, there is only change in dimensions. Okay, so I'm saying linear deformation. Okay, this is dimensional deformation. So let again we are saying a fluid element is here. Just a minute. Let we are saying this is our x direction coordinate system, this is y here, and this is our fluid element. Okay, and around, let we are saying this is our center O, this is A, this is B, this is C, and this is D. Then dimensions are, this is dx in the x direction, dy in the y direction. Okay, now again we are saying u, and u is the velocity in x direction and v is the velocity in y direction. But in this case, let I'm saying u is the function of x only, means you can only vary in x direction, and v is the function of y only, means we can only vary in y direction. Okay, then what's going on, let's check. So let's suppose on the face AB of this element we are saying this is our velocity u here. We are defining our velocity over here in the x direction on the face AB is simply u. You can see here the magnitude of u throughout same on the face AB, because u is not the function of y. This is not going to change in y. It can only change in x direction. So now let's suppose in on the face CD this is the magnitude, and obviously this is I'm saying larger than the face AB. Okay, and what is this magnitude? So let we are saying this is u plus del u by del x into dx. This is the velocity here. Okay, you can see here del u by del x is simply the gradient of change, And when we multiply this one by the dx, then this is probably the total change, that is del u by del x into dx of velocity. And we are saying this magnitude, so we are adding this change to the u velocity. So here the total velocity is u plus del u by del x into dx. So u is the only function of x, u is not the function of y here. Now let we are saying over the face AD, okay, we are saying over the face AD. So this is our velocity v. As v is the only function of y, so it will remain same throughout the face AD. But as we can see this one, this is the function of y, we can change over this y here. So let's suppose we are saying this is the magnitude of this velocity v over here. Okay, so what is this magnitude? So we can write this is v plus del v over del y. Now change in y into dy. Okay, this is the velocity at this face BC. Now from this diagram you can clearly understand CD velocity, or velocity on the face CD in the x direction, is greater than the velocity on the face AB. Obviously this differential velocity will try to stretch or try to increase the dimension of this fluid element in the x direction. Similarly, the velocity on the face BC is more than the velocity on the face AD, then this will also try to stretch or increase the dimension on the y direction. And as there are some velocity here also on the face AB and also on the face AD, so this element will also translate. So actually in this case what's happening, this element is translating, also deforming linearly, means this is translating plus its dimensions are also going to change over the translation. So let we are interested only in the deformation here, not in the translation. So let we are saying u and v are the 0, means the velocity on the face AB is 0 and the velocity on the face AD is 0. So when these velocity at the face AB and AD are 0, in that case this face AB can't move in x direction and this face AD can't move in y direction. Okay, because here we are saying this is 0. So here we are saying u equals to 0, also v equals to 0. So in this case AB and AD face can't move. So what is the velocity on the face CD? So as we are saying u is 0 here, so the differential velocity here, or velocity available at this point, we can say that this is equals to del u by del x into dx. Okay, this is the velocity on the face CD. And what is the velocity on the face BC? So obviously v is 0, here v is 0, so the differential velocity we are saying in this case, this is what part we are saying, this is del v by del y into dy. Okay, this is in this direction. So there are velocity on the face BC and CD, that's why this face will try to move and face AB and AD can't move. So in the time interval dt, this element is going to deformed linearly. The dimensions are going to change in this case and it will look like this one. Let's suppose we are saying this is our new element after the time interval dt. Okay, so this is A point, A is here, but B is now moved to B dash, C will move to C dash and D will move to D dash. Okay, and here that was the O, but the new O is here, around here. This is our O dash. So this element is deformed over the time interval dt. So what is the deformation in the x direction? So obviously the deformation in the x direction, we can say the distance d dash. Okay, so we are saying what is d dash? So what is the velocity here? Velocity is del u by del x into dx. This is the velocity and we want to check in the time interval dt. So this d dash will be equals to del u by del x dx into dt. You can check the dimensions here. It will be in mm, meter, or all these things. Now similarly, we want to check what is the linear deformation in the y direction. So you can say this one, this deformation will be equals to b dash. Okay, this deformation will be equals to b dash. So the velocity in the y direction, that we can say that there is no velocity on the face AD here, and on the face BC here the velocity is del v by del y into dy. So velocity is del v by del y into dy. This is the velocity. So in the time interval dt, this element is going to stretch or linearly deformed by this amount in the direction y. So this is in the x direction and this is in the y direction. Okay, so this how we can define the linear deformation. And if you are saying that is u and v are not 0 and it's having some value, in that case this element will also translate and deformed during the translation. Okay, so I think point is clear what is the linear deformation. Now next we will try to understand the concept of rotation. So third, we want to try to understand rotation. Okay, so that again we will consider. So I'm drawing here, so there is space here. So I'm saying in this case, let again this is our x-axis and y-axis here, and we are considering a fluid element over here again. So this is our fluid element, and that this around here is center. Same element we are considering again. This is O here, this is A, this is B, this is C, and this is D here, and dimensions are dx in the x direction and dy in the y direction. Okay, now let in this case I am saying u is the only function of y. Check the last case, I said u is the only function of x. I am saying in this case u is the only function of y, and v is the only function of x. Just reverse case. Here v is the function of y, in this case I am taking the v is the function of x. Okay, so just reverse cases here. So means the u can only vary in y direction but can't vary in x direction, and similarly v can only vary in x direction but can't vary in y direction. So that first we are saying that this is v here, okay, and v can only vary in x direction but it can't vary in y direction. So when we are moving over the x, let's suppose this is varying like that. Okay, this is here. So v is varying over the x. Okay, and let we are saying this value we are writing, this is v plus del v over del x dx. Okay, so you can see here v is changing over the x here, and I'm saying let this is our u, and this can only vary in y direction but not vary in x direction. But in this case, let I'm saying this is decreasing over here. Why I'm taking the decreasing case, I will tell you. So this I am saying, so this is the variation of u over the y. So this value you can write, this is that u minus del u over del y into dy. It is going to change over the y dimension and it is going to decrease, I'm saying that. So if you draw variation of u over the face CD, it will be exactly this one. Means here it will be u and here the value will be less, that is equal to this one, because you can't change over the x. Similarly, if you draw the variation of v over the face BC, it will be exactly equal to this diagram. At the point B the velocity will be v, and at the point C the velocity will be v plus del v by del x into dx. Means we can't vary over the y here. So we are defining this is the case here. So we can check what is the change of v over the x. Okay, so we can say this is our change, this value, this is the change. So this value we can say this is equal to this value. So we can say this is del v over del x into dx. Okay, this is the change. So what is the gradient? If this is the change, then what is the gradient? So we can say that the gradient will be equals to del v over del x. Okay, I am saying this is the gradient. You can check the dimension of this one. This is meter per second by meter. So this is per second. And if we are saying, let's suppose we are saying v equals to r omega, and we can say that omega will be equals to v by r. So v by r dimensions are simply per second, or we are defining this is radian per second. So actually these dimensions are in radian per second. Okay, these dimensions are in radian per second. Now similarly, so here we are defining that the dimensions are radian per second. Similarly, we can see in the y direction. So here we can say that is when we are moving in the positive y direction, then the gradient. So gradient here is actually going to be decrease. So the gradient is not going to decrease. The change is here is negative, this value, and we can say that this value is equals to minus del u by del y dy. Okay, so in this case the gradient will become minus del u by del y. Units of this one is also radian per second. Okay, now so as we are saying here, as we are moving in the positive x direction, in this case the change is positive. That is, in this case the change in positive x direction. So this value del v upon del x is in positive change or in positive y direction. Okay, similarly, when we are moving in the positive y direction, here the value is going to be decrease. So in this case this value is in negative x direction actually. Okay, let's check again. In this case, when we are moving in the x direction, change in positive y direction. So we are saying del u by del x is in positive y. But as we are moving in the positive y direction, here the change is negative. So this is in negative x direction. Now similarly, let's check in this case, when we are moving in negative x direction, means when we are moving from the face CD to face AB, then the value of velocity is going to decrease. So this is in negative change here. So means this negative change means this is in negative y direction, opposite of this one. Similarly, when we move from the face BC to face AD, here the changes are positive. So on this face, this will be in positive x direction. So this is positive here, so I'm marking here this is positive direction here. This is negative here, so I'm marking here this is negative here. Okay, so you can see this one, that is this direction of arrows will try to rotate this fluid element. Okay, as we can see here, this is a two-dimensional system, so rotation of this fluid element is going to be about the z-axis. It will try to rotate about z-axis. So we can write this is omega z, means rotation about z-axis. Okay, and this will be equals to the average value. What is the average value? So let first value is this one, that is del v by del x, del v by del x. Second value is minus del u by del y. So we are adding these two, so I'm saying plus minus del u by del y and whole divided by 2. We are taking the average value of this one. So this plus minus is going to be minus here, so we can write this is 1 by 2 del v over del x minus del u over del y. So this is providing what? This is providing rotation about z-axis. Similarly, we can show that is omega y. What is the rotation about y-axis? If this we are considering this element is 3D. So rotation will be in all three dimensions. It is possible in all three dimensions, about the x-axis, about the y-axis, and about the z-axis. So we define this is the rotation about z-axis. So you can write here similarly like that. So this will be equals to about y. So if this is z, then you are saying this is x, then this is y. So if this is y, so you can say this is will be x here, sorry, z here, and minus this will be y here, and the respective y value is v, that is over here, and the respective x value is over here. So if this is y here, okay, so sorry, this is not z, this is x here actually, sorry, this is x here. So x is here, so here it will be u, z is here, so here it will be w. Similarly, we can define omega x, so this will be 1 by 2. So this is x, so we can write this is y, minus this is z. So respective value of z is, we can define here is the w, respective value of y is, we can define here it is v. So this is the rotation about x-axis, about y-axis, and about z-axis. You can imagine a cubical fluid element that is in the random flow of the river. So when the river is flowing, in that case the element will try to rotate about all three axes. So we defined that rotation is about z, x, and y. So what is the total rotation or net rotation we can want to define? So this is a vector quantity, so we can say that there is omega will be equals to omega x I cap, omega y j cap, and omega z k cap. This is the total rotation. So this is the total rotation we are defining here. We have simply put the value of omega x, omega y, and omega z here. Now as we know that v, velocity vector v, we can write in three dimensions, that is ui vj wk. So this quantity we can define like that. We can define this is the curl of v, or simply this is curl v, or this is del cross v. Okay, this quantity is termed as curl v, that is this is the cross product of del and v here. What is del? Del we are defining, del is equals to del by del x I cap, del by del y j cap, and del by del z k cap. This is our del here. So this we are defining, this is the curl of v. So we can solve this one, curl of v, this is the vector multiplication here. So we can write this is I j k. The value of del is del by del x, del by del y, del by del z. The value of v is u, v, and w. Okay, so this multiplication or vector multiplication will exactly provide this value. This will provide exactly this value. Okay, so means we can write omega is equals to 1 by 2 curl v, or 1 by 2 del cross v. So from here we can say that if for a given flow field or given velocity vector field, if curl of v is 0, then obviously omega is going to be 0. Okay, if we are saying if curl of v is 0, then omega will be equals to 0. In that case we can say that that flow field will be irrotational flow. Okay, if curl of that velocity vector field is 0, in that case we can say that is omega is going to be 0, that is that flow will be irrotational flow. Point is clear? Now here we can understand some more about the rotation. Let's suppose we are considering a river here, Let's suppose this is the river bank, and water is flowing over here. In that case, if we draw the velocity distribution, in this case, we are taking this is the cross section of this river. So obviously from the no slip condition at these river banks, the velocity will be 0 and the distribution will be parabolic, and it will look like this one. It will look like this one. Okay, this is the velocity distribution of this field, velocity vector field. You can say this is the velocity vector field here. So when you put, let's suppose I'm putting some stick here. In this case, you can see here the velocity is more and here the velocity is less. So in that case, this stick will try to rotate, and it will start to rotate actually, and this will rotate in this counterclockwise direction. So this field is rotational field. And similarly, if you put the stick here, in this case, here the velocity is more, here the velocity is less, so this will try to rotate in this clockwise direction. So this is presenting the curl property of this field. But like if we are saying there is if curl of V is 0, in that case the field is not rotational. In that case the field is termed as irrotational field. Okay, like if we are putting this stick in between this one or exactly at the center, that I'm using a different color here, exactly at the center, in that case both side vector has same velocity. In that case it will not rotate, it is simply moving in straight line here. Okay, so I think you can visualize from here what is the curl property of this one. So this is how we can calculate or easily define the rotation. Now our third case is shear deformation. So sorry, third not, it's the fourth case. Fourth case is shear deformation. Okay, so let's try again. So again we are saying this is our axis system, x and y. This is x, this is y, and here we are saying this is our fluid element. This is A, this is B, this is C, and this is D. And let's suppose we are saying this is our center, that is O here. Dimensions are dx and dy. Okay, again I'm taking the same case, means I'm saying u is the only function of y, only function of y, and v is the only function of x, as in the case of rotation. But in rotation I provide that is u is decreasing when we are moving in positive y direction. Okay, but in this case I will take both v and u are increasing, or you can take both u and v are decreasing. But in rotation we define v is increasing, u is decreasing, or you can take u is increasing, v is decreasing. In that case the direction of rotation is going to be changed. It may be clockwise or anti-clockwise, that's all. Means but both will be anti, means if one is increasing then otherwise is going to be decreased. But in this case both are either increasing or decreasing. Okay, so here we are saying this is v here and it's increasing over the x. So this value become v plus del v over del x into dx. Okay, and this is u here and it is also increasing over the y, means both are increasing in this case. So this will be equals to u plus del u over del y dy. Okay, in this case both are increasing, and as u is not going to change over the y, so on the face BC this will be same here, and as u is not going to change over the x, so over the face CD it will be same here. So what are the velocity gradients in this case? we can check here and we can define this difference or this gradient is actually positive here, that is del v by del x. This is a gradient and this is positive here. So positive here means this is in positive y direction. Okay, and in this case this is also positive over the face PC here, this value. So I'm saying in this case the gradient, I'm not saying this is the value, actually I'm defining the gradient here. So gradient here is also positive, that is del u over del y, and this is also positive. Positive means this is in positive x direction. So this is in positive y direction, this is in positive x direction. Now on the face AB, when we are moving in negative x direction, so v is going to be decreased. So this is the gradient is in this direction is negative, so this is in negative y direction. And over the face AD, if we are moving from BC to AD here, this is also going to be decreased, so this is also in negative x direction here. Okay, so you can see the vectors here, so direction here, so this is in this direction, so this is in this direction. So in this case this element will not rotate. Actually in this case the shape of this element is going to be changed and it will look like this one. So if I am saying this is the diagonal of this element here, this is this diagonal. So over the time interval the shape of this element will be look like this one. It will look like this one. The angle or position of this is going to be changed here. Okay, so in this case the shape of this element is going to be changed here because this direction will try to squeeze in this side, this direction will try to squeeze in this side, this will try to squeeze in this side, and this will try to squeeze in this side. So in this case there is no rotation, in this case there is a deformation here. Okay, so this deformation is in shear plane, sorry, that is in the 2D plane. So we can define that is shear deformation in xy plane. Again we are taking average value. So in this case both are positive, so I am simply adding this one, that is del u by del x plus del u by del y. So this is the deformation in xy plane. Similarly you can define deformation in yz plane if this you are considering 3D here. So this will become what? This is y and this is z here, this is del w, this is del v, and in zx plane you can define 1 by 2, this is z here plus this is x here. For the x there is u, for the z there is w here. You can see here xy, so xy, yz, yz, zx, zx, and for xy, so y is here, so respective value v is here, x here, so respective value here. So the total deformation you can define, this is vector sum of xy, then vector sum of all, this is yz plus vector sum of zx. Okay, so I think this is clear. So guys, if you are like the lectures, so please like the video, subscribe the channel and comment your doubts, and please share the knowledge as much as you can. Thanks guys, take care of yourself, see you soon, thanks again.